3 is on the measures of relative standing or position and box plots. A z-score. This is a standard score or a standardized value. It's the number of standard deviations that a given value x is above or below the mean. It converts a value to a standardized scale. And it's always bolded, capital letters, everything, always rounded to 2 decimal places. The sample z-score, well, I should say the overall z-score formula takes the value, the data value, subtracts the mean, and divides that by the standard deviation. The sample z-score takes x minus x bar divided by s, and population z-score takes x minus mu divided by sigma. This is expressed with no units of measurement. The data value is significantly low if its z-score is less than or equal to -2, or significantly high if its z-score is greater than or equal to +2. If the value is less than the mean, the z-score is negative. Likewise, if the value is more than the mean, z-score is positive. And one of the best things to be using the z-score for is to compare data values from different data sets. The mean of z-scores is always 0, always, and the standard deviation of z-scores is always 1. So, for example, we want to know which of the following data values is more extreme relative to the data set from which it came. The 4,000 gram weight of a newborn baby among 400 weights with sample mean x bar of 3,152.0 grams and sample standard deviation s of 693.4 grams. The 99-degree Fahrenheit temperature of an adult among 106 adults with sample mean x bar of 98.20 degrees Fahrenheit and a standard deviation of s of 0.62 degrees Fahrenheit. So for the z-score of the weight, it takes 4,000 minus 3,152 divided by 693.4. Toss that into a calculator, you get an answer rounded to 2 decimal points of 1.22. For the temperature, the z-score of that would be 99 minus 98.20 divided by 0.62. Toss that expression into the calculator and you get an answer of 1.29. So 1.29 has a higher z-score, and as such, 99 degrees Fahrenheit is the more extreme value relative to its data set. When it comes to these z-scores, we can have a data value that's significantly low if its z-score is less than or equal to -2, as we could see from this graph, or significantly high if its z-score is greater than or equal to +2. And if it's between -2 and +2, then the value is not significant. Another example of these z-scores is the lowest platelet count in the dataset, one body data set, is 75, measured in 1,000 cells per microliter. Is that value significantly low? We want to assume that platelet counts have a mean of x bar of 239.4 and a standard deviation of s is 64.2. So the z-score would be 75 minus 239.4 divided by 64.2. This makes -2.56. So that is less than -2. Right? So because of that, yes, it is significantly low. So the percentiles, the same idea of this is the specific types of quantiles and fractiles. A percentile is a measurement of location denoted by p sub whatever location we want. So P sub 1, P sub 2, all the way up to P sub 99. Which divide a data set into 100 groups with 1% of the values in each group. So P sub 50 is the 50th percentile, or the median, which we have seen the calculation of already. We would round to the nearest whole number. That is where we take for the percentile of value x. This is the number of values less than x divided by the total number of values times 100. The total number of values in the data set is n, the sample size. The percentile being used is k, and p sub k is the kth percentile. The location of the position of a value is denoted by a capital L. So, for example, below are the 40 cotinine measures, down here, and nanograms per milliliter of smokers from the dataset 14 passive and active smoke, and they are listed in order. We want to find the percentile for the cotinine level of 198 nanograms per milliliter. So 198 I have circled in this table down here, and we have a total of 22 below it. So 22 divided by 40 times 100%. This gives a percentage, of 55%. So this particular percentile is at P sub 55. For the value of the 33rd percentile, this would take L is equal to 0.33 times 40, which gives us a value of 13.2. But because that has a decimal in it, we round that up to 14. So 121 is the 33rd percentile, since we would then in this case then count a total of 14 of these entries to get to 121 on here. So the overall idea of converting the kth percentile to corresponding data values, we first sort the data in order of lowest to highest. We compute the position as k divided by 100 times n. And if we have a whole number, then the value of the kth percentile is midway between the nth value and the next value in the sorted set of data. We find P sub k by adding the nth value and then the next value and dividing the total by 2. If it is now a whole number, then we change L by rounding it up to the next larger whole number. And the value of P sub k is the nth value continuing when we count from the lowest up to that point. And now for an example of what that means, we can look at the sorted pulse rates to find the 25th percentile. So L here would then be 25 over 100 times 40. This gives us a value of 10. And the 10th value from that sorted pulse rates, this is based on P sub 25. This would be 86 plus 87 divided by 2, which makes 86.5. As we can see from this cotinine levels down here on this table, we took this 86 here, and the value above it, 87 over here, which is where those came from. Quartile is a special type of percentile denoted by Q sub 1, Q sub 2, and Q sub 3 for the first, second, and third quartiles. They divide the data into 4 groups with about 25% of the data values in each group. So Q sub 1, the first quartile, this is the same value as P sub 25. Separates the bottom 25% of the sorted values from the top 75%. And the second quartile, Q sub 2, is the same thing as the median, P sub 50. Sorts the data in half, or less than or equal to the value. Q sub 3 is the third quartile, that's P sub 75. separates the bottom 75% of the sorted values from the top 25%. Technology, though, tends to calculate these quartiles differently, so do keep that in mind when computing these. Some special calculations involving quartiles and percentiles. Interquartile range is q sub 3 minus q sub 1. The semi-interquartile range is q sub 3 minus q sub 1 over 2. Mid-quartile is q sub 3 plus q sub 1 divided by 2. And the 1090 percentile range is the 90th percentile minus the 10th percentile. We have a 5-number summary as a type of data analysis that we could use. And that consists of the minimum, first quartile, Q1, median, third quartile, Q3, and maximum. A box plot is basically a graphical version of the 5-number summary. Another word is box and whisker diagram. It's a graph of a dataset consisting of that 5-number summary, extended at a number line, such as this example here, which is of a symmetric box plot. And as you can tell, we could determine the shape of the distribution by just looking at this box plot. We first, though, in order to build the box plot, we need to find the 5-number summary, construct a line segment extending from the minimum to the maximum, connect a box connecting Q1 and Q3, and then note where the median or Q2 is. And based on the continent measures that I have down here, we're going to calculate the 5-number summary. Doing so gives a minimum of 0, Q1 is 86.5, median is 170.0, and Q3 is 251.5, maximum is 491. And we could produce this box plot, which definitely shows to be a skewed rate distribution. For the data set 1 biodata data set, the pulse rates of men and women, we constructed a box plot for these two different sets of pulse rates down here. This bottom one appears to be, for the males, appears to be symmetric. While the top one here is slightly skewed left. Right? The box is off-center to the right, which means that the whisker here to the left is longer for the female one, and this box has a bigger area here on the left side than the right side. So this one's skewed left. When it comes to these box plots, we can make a modified box plot by removing the outliers. So we first need to find the quartiles, find the interquartile range, take 1.5 times the interquartile range, and add it to Q sub 3 and subtract it from Q sub 1. If it's above Q sub 3 plus 1.5 times the interquartile range, then it is an outlier. If it's below Q sub 1 minus 1.5 times the interquartile range, it is also an outlier. And these two are referred to also as fences. A modified box plot, though, is a box plot that excludes these outliers. So, for example, using the pulse rates of males of the dataset 1 biodata dataset to construct a modified box plot. The 5-number summary is 40, 62.0, 68.0, 76.0, and 104, all in beats per minute. So the interquartile range would take 76 minus 62. That gives us a value of 14. 1.5 times 14 is 21. So for the lower fence, we're taking Q sub 1, so 62 minus 21. That gives us 41.0 beats per minute. And Q sub 3 plus 1.5 times the interquartile range is 76 plus 21, so 97.0 beats per minute. And this box plot down here removes the outliers of 40, 102, and 104. And now the highest pulse rate that is now an outlier is now 96, and the lowest is 42. Thank you.